Okay, good morning to everybody. We have the pleasure to have with us Luis Strigari, and he will start today's talks with neutrino physics and dark matter detectors. Thank you very much for being here.
Oh yeah, thank you. Thank you for the invitation and for the very nice workshop. It's been a pleasure to have some good interactions with people the past week or so, and look forward to more in the next few days. So the title of my talk is Neutrino Physics at Dark Matter Detectors, but the talk will be like a little bit more broad than that. It'll be kind of how the general theme will be how some traditional topics in neutrino, astrophysics, and terrestrial physics kind of carry over to large-scale next-generation detectors that are going to come online here in the next few years, and one of them being sort of like traditional WIMP dark matter detectors, as you see here. So this will hopefully be kind of like a broad overview of the topic, as well as sprinkled in some things that I've been working on, in particular with some graduate students at A&M. So we just started here this morning. I know everyone probably knows this figure here, but let's kind of use it to orient ourselves going forward for this talk here. So here, of course, we see models for neutrino cross-section as a function of energy over a vast range of energy scales. And on top of this figure, you see the different sorts of sources that are known of neutrinos, both terrestrial and astrophysical. Of course, we have neutrinos from the Big Bang that we believe are there. We had some discussion earlier this week about trying to detect these neutrinos and all the interesting work that's been going on along these lines, all the way up to sort of the highest energy neutrinos that are produced in sort of the highest energy astrophysical phenomena in the universe, accretion disks around black holes and so forth. So of course I can't go through all this in one talk. It would not be wise to do that. What I'm going to kind of do here is focus the effort on a range here. So that's the pointer, right? In sort of this kind of medium energy range of several to tens of mega electron volts, and kind of give you a sense of what physics opportunities are available here going forward in this energy regime, both sort of using neutrinos from astrophysical environments, as well as neutrinos that are produced here in the lab on Earth. So that's kind of going to be the general way that this talk goes here for the next 20 minutes or so. And I'm going to start by talking about astrophysical opportunities for neutrinos in this energy regime. Now, I don't think there's been too much talk this week, at least, about solar neutrinos. So let me kind of just give you a review of what we know about solar neutrinos at this point. So on your left there, you see the sort of traditional neutrino spectrum from all the sources that produce neutrinos in the center of the sun. The PP chain, of course, has the largest flux, and those neutrinos come out at the lowest energy. The most accessible component that is detectable is the boron-8 component here, which is relatively low flux, of course, but is high energy. And now, really, as of just a couple of years ago, Boraxino collaboration has come out with some kind of their more or less, I think, final results for their fits to the entire solar neutrino spectrum. This is actually really, very, very interesting analysis, because they were able to perform a multi-component spectral fit to obtain measurements of pretty much all the dominant components of the solar neutrino flux, including, for the first time ever, really get a quote-unquote direct measurement of neutrinos from the direct PP chain, which produces about 99% of the energy in the solar core. They're actually less sensitive to this boron-8 component that experiments like Super K and SNO were. They're more sensitive to neutrinos from sort of the lowest energy pieces of the PP chain, including these PPs, as well as beryllium-7 here, this line here. They did a lot of interesting physics studying this line here. And also, I should also mention that they were the first experiment to detect neutrinos from the CNO cycle, sort of the combined, these purple curves here. They made a measurement of neutrinos from CNO. Of course, that's important because this tells us something about what's going on ultimately the metallicity in the solar core, and there's just a very small amount of energy that gets produced in the sun due to CNO cycle. Okay, so understanding those neutrinos actually, of course, tells you a lot about, possibly what's going on, how the sun produces its energy in the very central regions. And of course, there's kind of long-standing issues about the solar metallicity. I won't really go into those in too much detail, but this actually tells us, in addition to learning about neutrino physics, we can actually, do a lot of interesting solar physics from this. So this is kind of the lay of the land at this point with solar neutrinos. And this is actually, like I said, this is actually relatively new results, right? These are just came out a couple years ago from Borexino. Okay, so this is not, of course, going to be an advertisement for like any particular experiment, but I just want to like show these experiments here because it kind of puts what I'm going to talk about here in context. So we have in the next decade or so, we have kind of a sort of a wide range of different large-scale neutrino experiments that are going to come online. The Dune experiment, Argon based on Argon DPCs. Of course, we've had some discussion about this past few days. So that's the detector technology used. Hyperkamiokande, larger version of Super Kamiokande, basically. Juno, large-scale liquid scintillator, and I put on here a generation 3 xenon dark matter detector, TPC, because ultimately that will also be a neutrino detector. And I think I just like to put this slide up because it just kind of tells us that we have like lots of different types of coverage in terms of different types of quote unquote beams that can be used for detection at these types of experiments, as well as different types of detector technology that all these use. So these can actually all be like quite complementary in the neutrinos that they study from the different sources that we're going to talk about today. Okay, so I'm going to talk a little bit probably about all these experiments at some level, kind of very broadly, and like where the physics possibilities are here. Okay, so kind of starting with the solar neutrino game. Of course, we focusing in on a xenon experiment for the time being. This might actually be, in some sense, sort of the next like big opportunity for solar neutrino physics. And you can kind of very clearly see that here in this paper published a couple years ago by the Xenon 1-ton collaboration, where they set their WIMP limits here in sort of this traditional WIMP region of parameter space. And what I really just want to get across to you in this figure here is if you kind of look where the neutrino floor or fog or whatever is meeting the WIMP limits, it's kind of meeting it right here in this regime where the boron 8 component of the solar neutrino flux is predicted to exist. And this interaction is going to happen according to the coherent neutrino scattering channel, which I'll actually talk a little bit more about detail about that via terrestrial experiments later on in the talk. But this is actually going to be, interesting because this will be like the first time, of course, dark matter detector is able to measure the solar neutrino flux, and actually this gives you a brand new channel to measure the solar neutrino flux through as well. Okay, so this would be the first time via astrophysical sources detecting coherent neutrino scattering. So this is actually probably likely to happen at some point during the lifespan of a generation 3 dark matter detector. And here you kind of just like zoom in on all the more detail on this particular region here where we're looking at. The experimental challenge here is getting your xenon thresholds to low enough energies where they can get acceptances to actually study this. But if that's possible, then there's a huge flux sitting there for them to study. So we're going to go over some physics implications of that. In addition, actually, if you have a large-scale xenon detector, it's actually a multi-channel, multi-purpose solar neutrino detector. PP solar neutrinos, that lowest energy component, will just do plain old elastic scattering of neutrinos from the sun. And that will presumably make a signal in a dark matter detector. Well, of course, in here you see sort of the traditional separation that these detectors do in terms of their signals, the S1, S2 components, and sort of your nuclear recoil band sits here in this pink regime, and then the electron recoil band sits in that sort of greenish regime. And so the idea here is if you kind of dig through this data, you can actually see possible contributions from elastic scattering of PP solar neutrinos. Of course, the traditional WIMP signal would sit right in here, right? And if we're talking about detecting boron-8 through coherent scattering, it would be here. But it's very likely the first signal that these things see will be via the electron recoil band. And in fact, just very recently, within the past year, the Panda X collaboration has actually come out with some results. I forgot exactly the sigma at which they made this measurement. Actually, it was probably, I think it was like something over 1 sigma. So it was still, the sensitivity still isn't great, but they actually did an analysis where they had, like I said, a very low significance detection of neutrino electron elastic scattering via the PP chain. Right now, the issue, they're kind of buried in sort of experimental backgrounds, as you can kind of see here from this figure. But this, of course, will, as statistics continue to improve and backgrounds continue to get understood at the appropriate level of detail, this signal will actually start to appear. So really the way that I like to think about this kind of detector here is this is basically, if you will, in some sense, a next generation like Boraxino type detector, right? Boraxino did that multi-component spectral fit of the solar flux. And so something actually very similar can be done with a xenon detector like Panda X, LZ, xenon n-ton. But the interesting thing about this is this will actually bring us to like very low, to lower energy electron recoils than Boraxino is able to access. So this actually gives us a measurement kind of in a fundamentally new regime of this process. Yes, Bryce. The spectral features. So these are backgrounds. These are, let's see. So I think the main background, so here's Krypton here, which is a background. So this thing here is going to be this process here. I don't know what xenon 133, that might be like a decay, a beta decay or something. Yeah. So this thing here, just to get us, this is another peak here. I'm not sure what this process is actually, to be honest with you. Yeah, I'd have to look at the details. Okay. So yeah, right. So this is right. We have data, and I think we're going to expect some new results here going forward in these types of experiments. And so the question is, of course, like what kind of physics can you do with these types of measurements? And that's the question that we want to go after. So here's once again a figure that probably everybody's familiar with. I don't know that we've actually seen this in the past few days, so I'll kind of go over it a little bit. So this is the solar neutrino survival probability as a function of energy. On the left part at low energies, of course, you have a sort of standard vacuum oscillations that are relevant for the PP and beryllium-7 components of the flux. Then you have a turnover to a regime in which matter-induced oscillations start to take over. And we have the MSW model for this flux here, right? Which seems to work pretty well. And in some sense, okay, this solves our problem, if you will. But you always kind of like to look at this figure a little bit. Hey, like, look, if that line wasn't there, I mean, we don't like have like super precise measurements of this at this stage, right? Like, I'm not like advocating that the model's wrong. That's not like, but the theory model is like, oh, great, we've got it right, but the data is like, okay. So I think there's still like a good deal to do here, and I haven't actually shown it on this figure here, but if you actually do like a generation 3 type detector, you can actually via electron scattering, you would actually get like a much very precise measurement of the survival probability. Actually, over here, sorry. Okay. Mhm. Yeah. Yeah. So I don't know. I took this from I think the recent Boraxino paper, so I don't know exactly what they did to generate the line, but I think this, if you actually take the sort of standard model neutrino parameter, like the range of the delta M's and the thetas, you kind of get something pretty thin like that. But Mhm. Oh, that's probably true. Yeah. Yeah. Okay, that's fair. Yeah. Yeah, so I guess the question of like what probably what we're getting at here is what's your sort of theoretical priors that are going into this analysis, and yeah, and so that's kind of up for debate. Okay. Okay. So now I'm going to so this could kind of gets the next couple of slides here where I'll start editorializing a little bit on this topic. So this is the neutrino survival probability, right? The electron neutrino survival probability as a function of energy, right? It would be nice, of course, to do appearance probabilities as well for the different flavor components here. And so here's a figure made by my student Natasa recently, and this is kind of a standard analysis of using the sort of the best fit neutrino oscillation parameter. So here's our electron neutrino survival probability curve, and we have the other components here, and actually like a relatively large component of neutrinos from the sun show up, in the tau flavor, and we haven't had an experiment at the moment that's had sensitivity to kind of separate between these two flavors. But the idea is maybe, going forward, if we do like high precision measurements of the solar flux, maybe we can actually think about, identifying channels where something like this could be possible. So kind of with that question, we kind of started just doing some general thinking and exploration about, what could be possible going forward. And that's where sort of these large scale neutrino detectors kind of come in with in examining their capabilities. Okay, so we started off this sort of exploration just thinking about xenon, coherent scattering of xenon of neutrinos from boron 8 in a xenon detector. And I'll talk a little bit more about sevens. Indeed, I'm kind of going backwards with sevens a little bit, right? I'm talking about corrections to the sevens process first before I actually talk about it later. But the idea here is if you get kind of percent level measurements of the solar neutrino flux, you can possibly be sensitive to sort of just regular old standard model like radiative corrections to the cross section here. And here's an example diagram which contributes to this process. And this is like not new, right? These calculations are not new. They go back like a long time, right? And this figure you can kind of tell is from the 1980s. So we actually went through the numbers. Actually, when I'm not really thinking about this in terms of like, detecting this process, I'm thinking like, can we use the phenomenology, right, to go forward and sort of learn about, flavor composition of the solar flux? And that's what we did here. So we kind of went through and said, can we, is it possible to statistically extract out, all the different flavors of the solar flux? And it's possible, to maybe this is, we didn't really go through all the details of the simulations, the experiment at this stage, but if we kind of drop our thresholds for our xenon detector low enough, below a kilo electron volt or so, that rate kind of exponentially rises here. So if you can kind of get on this like sort of steeply increasing part of the curve here, if you can drop your thresholds low enough, then you can get thousands and tens and thousands of events where you can possibly think about doing this separation where you can actually you're sensitive. Statistically speaking, we heard a talk yesterday about trying to detect tau neutrinos at higher energies, event by event, or statistically this would be kind of a statistical detection of the tau component of the neutrino flux. But this is actually something that's possible, and we actually went through a few more details in this paper I'll refer you to in terms of the statistical analysis. Well, it really just all depends upon your threshold. Yeah. So if you drop it down, if the detectors can drop down to a few hundred electron volts threshold, this is something that's actually possible. And experimentalists said we can actually. I mean, this is not impossible. If a signal like this is there, then they. Oh, sorry. Yeah, these are the different contributions from the different flavors. Actually, I'm actually probably not going to remember which one is which here, but then this is just the total composition. And the lines here, kind of the dotted, the solid lines give you the standard model contribution. Well, the tree level contributions, and the dashed or dash dot or whatever they are give you the corrected version. So you can kind of get a sense of how that works. So this, yeah, you're looking for like a small signal, and this is a statistical separation, right? So think back to like Borexino, right? Borexino didn't say, that event was like, from CNO, that event was from PP, right? They kind of just they did a spectral fit to the whole game, right? So that's kind of the way that we're thinking about this. Actually, I should also mention too, this would be like a way to measure tau neutrinos, right, at low energies. Right, so we talked about, why tau neutrinos would be interesting to measure at higher energies, and the only way, of course, you can create tau neutrinos, well, yeah, I mean, through mixing, right? That's the dominant way at these energies. So this would be actually so this is actually this is kind of one reason why I think pursuing these types of studies is interesting. Probably went a little bit long on the first part of this talk here, but I should just actually mention a similar analysis, similar in spirit, was done around a similar time by these couple of authors here, applying this type of thought process to Hyper K and Dune. And you have, so they utilize not coherent scattering process, but they utilized charge current elastic scattering of neutrinos. Oh no, I'm sorry. Yeah, the scattering of muon and tau neutrinos on electrons, and the corrections that get induced to this at the few percent level. And in this way, you can kind of also do a statistical separation of the tau and the mu neutrino flux using these types of experiments. And they did some analysis where you actually can maybe get some sensitivity to delta CP because you're looking, you're sort of specifically unpacking what's going on here in the mu tau sector as well. So I'll make a final. So this is basically what we can do in the future. So this kind of just like got us thinking. Okay, we're like, this is, these experiments are going to happen at some point. We're like, where are we right now, right? In terms of limits on 3-flavor solar neutrino oscillations with the present data. And we know, of course, the data is not sensitive enough at the moment to do mu tau separation. But we actually went through this exercise, and I think she submitted this paper here at some point this past week. So we actually just went through and looked through the Borexino data and, applied like a full three-flavor model to this analysis and use this elastic scattering channel to look at this. Now this plot's like a little bit busy, so basically imagine that this is the probability, the survival probabilities, right, for the electron in sort of the X component, which is the mu tau component. You can kind of see here that here's kind of where our present data live, sort of in this band here, for a 2-flavor oscillation model here on your left. You can kind of see at the moment we're kind of perfectly consistent with unitarity in the solar neutrino sector. Of course there's a wide range that's possible. And this is coming from a fit to Borexino, specifically beryllium-7 data. You can actually just go through the exercise and do like a full 3-flavor model. Okay. And that's what we have here in the figure on the left, where we have the appearance probabilities for tau and mu. Okay. And like I said, this plot's like a little bit busy, but you can kind of do a similar analysis, assuming that, just very, very phenomenologically speaking, assuming that the mixing is whether you're full unitarity in the mixing or not. And kind of the long story short here is that if you had an experiment that was like maybe about a factor of 30 times exposure larger than the current Borexino, similar type of experiment, then you could actually start to probe some sort of phenomenological non-unitarity models that are like still allowed by present data. And so the good news is like there will be an experiment that is about that size, similar in spirit to Borexino, which is Juno. And so this is kind of this is really type of analysis I think that could be thought about with that experiment. Now we didn't do it in the context of Juno because that would require going through and really understanding their projections for their backgrounds. But if you actually look at this, something like this could be possible going forward. So kind of like a long story short here, for the past few minutes, what I've been kind of just motivate sort of different scenarios for what can happen for precision measurements of solar neutrino flux going forward. Okay, how much time? Pipe time. How much time? 1 day. Okay, I'll try to stay official here. Okay. Yeah. Okay. So I do want to get to some points here later on. What other issues can you think about? You can think about when you make precision measurements of solar flux. You can think about time variability of the flux, and this has actually been measured by a couple experiments based, the flux changes based upon the eccentricity of the Earth's orbit. That's really nothing new. But actually, this gets kind of interesting when you think about dark matter detectors, right? Because there's the annual modulation that's expected to be predicted in the dark matter signal. And that's going to start competing with this modulation that comes in from the solar neutrino flux, especially if there's no dark matter signal that appears before you get down to the neutrinos. And the interesting thing is, like, the dark matter annual modulation is predicted to be more or less perfectly out of phase, right, with the solar flux. So we're kind of getting to an interesting phenomenological range here. Not only just trying to see the neutrinos, separate them from dark matter, but you have multiple signals that are varying through the detector. So this actually makes for kind of an interesting statistical problem. And in a couple of recent papers, actually went through and tried to figure out how you can statistically extract those signals with the time variability. Okay, so kind of speaking of time variability, I want to spend a couple minutes here on atmospheric neutrinos, and then I'll kind of finishing up talking about some terrestrial sevens applications. So we had a few talks about atmospheric neutrinos here. So here's kind of the spectrum, and this I think is a figure from Super K. And kind of what I just want to point out here is that we've had lots of measurements over the range of energies here. Sort of in this very low energy regime of the atmospheric neutrino flux, there's actually lots of interesting physics in astrophysics that starts to really affect the signal. And we don't really have too precise measurements at that scale. Okay, so the reason I'm kind of focusing on this scale here is because these types of detectors that I've been referring to actually will be sensitive to neutrinos sort of at these energies. And of course, where do the atmospheric neutrinos ultimately come from? They arise from cosmic rays, right, which are hitting the atmosphere of the Earth and then producing neutrinos. And those cosmic rays at these low energies here. So here's the kinetic. This is a cosmic ray spectrum measured. I think this is measured by Pamela over the course of the entire solar cycle. And you can kind of see at low energies here, the cosmic ray spectrum modulates due to the solar cycle. So the question is, does that modulation actually carry over? Well, it's predicted actually, you're right, carry over to the neutrino spectrum. But this has not officially, this sort of time variability of neutrinos at these energies has not actually been discovered yet. Super K, I think, has 1 or 2 sigma limit on this process. But the interesting point here is also, in addition to the time variability, the flux depends upon sort of the latitude of your detector due to geomagnetic effects. And sort of different, depending upon where your detector is, you kind of access neutrinos from different pieces of the cosmic ray spectrum. Okay, so for example, if your detector at a high latitude location like SURF, or relatively high latitude location where Dune would be, you access neutrinos from sort of this lower portion of the cosmic ray spectrum, right? Gran Sasso and Kamioka, right, accesses neutrinos from relatively high energy component of the cosmic ray spectrum, and just basically based upon where it's sitting on the Earth. And this actually requires simulating the atmospheric neutrino flux at these different locations, which actually gets to be there's lots of complications that actually go into this. So kind of just the point I want to make, here's a bunch of busy lines here. Really, the point I want to make here is, if you have a xenon dark matter detector, the neutrinos that'll show up there. Actually, the neutrinos that'll show up there show up from the very lowest energy portion of the atmospheric neutrino spectrum, right? And that's a convolution, basically. Where your detector is, but it's also the channel through which you're detecting neutrinos, which is coherent scattering, right? So the kinematics actually dictates that you're actually sensitive to neutrinos below 100 mega electron volts at these detectors. And so we actually, in going through and trying to do the neutrino floor calculation, we were actually really sensitive to this, but there was really no great predictions for the neutrino spectrum at these low energies. Sort of the classical spectrum that's used are these results from Honda, but there was no sort of extrapolations down to the energies that we were looking at. So we actually tried to work on this calculation a little bit and continue this to low energies. But the idea here is, if you did measure this spectrum, right, this would be the first measurement of very, very low energy atmospheric neutrinos. And there are some sort of BSM and applications that can be thought about here, but right now, sort of the astrophysical systematics are still relatively prohibitive. So kind of making this measurement, I think, is even interesting to begin with, and that's kind of just the point I want to get across with this figure here. One final point here, once again, another busy figure. And my 5 official minutes are running out pretty soon. But I just want to say, like, you can actually make this kind of measurement at all the kinds of experiments I'm talking about. Dune, right? Once again, Dune will access cosmic rays at this relatively low energy regime. Hyper-K will access cosmic rays, and Juno will measure hyper-Ks that are access neutrinos at a relatively larger energy range. So the idea here, I think, going forward, one could think about is like making sort of differential measurements of this at the different locations. You can actually maybe learn about neutrino and cosmic ray physics, as well as like the other elephant in the room is if you want to try to do neutrino oscillation parameters with atmospheric neutrinos, really you do have to have these effects in because this is a systematic effect in the long term to understand sort of the where the flux is coming from. And we did have a paper a couple of years ago where we actually went through the details of this analysis. Okay, so this is astrophysics. Let me, for the final couple minutes here, let me talk about sort of terrestrial measurements. And I'm going to focus a little bit on coherent scattering and some interesting thoughts about how these, or what I think are interesting thoughts about how these experiments tie in a little bit to what I was previously talking about, as well as applications they have in their own right for searching for new physics beyond the standard model, or just verifying what we think we know about the standard model neutrino processes. As you may know, there's lots of experiments that are searching for sevens these days. The one that's actually measured it at the moment is a spallation neutron source at Oak Ridge, particularly the coherent experiment. I've been talking about measuring it at a xenon dark matter detector. It's also kind of the next holy grail in the sevens game here is trying to measure it at reactor experiments at much lower energies. Typically, these are like more plagued by experimental backgrounds, so it's harder to measure. But I'll focus here on the measurements that have been done with by the coherent experiment at the spallation neutron source. And this is, of course, using a stopped pion beam. And as of right now, they have 3 measurements of the cross section. So this is the total neutrino cross section as a function of neutron number of the nucleus. And this is kind of a famous figure that they show. So they have a measurement on an argon target, a cesium target, which was the first measurement. And then the very, very new results that came out, I think, for neutrino last week were the germanium results, which they detected a signal based upon about 20 events scattering in germanium. So the game here, just what I want to get across here is that, the idea here is, here's the standard model prediction. There's some form factor issues that you have to deal with at these energies. And sort of the idea here is if you're kind of on this green line, then then you're consistent with the standard model. If not, then that gives us something to think about. At this stage, you might see, okay, if you squint a little bit, these measurements might be like a little low, but we might be kind of in a statistics limited regime at this point. So for my last couple slides here, I just want to talk about flavor separation and from the solar flux. So we can actually kind of do something similar here. Of course, it's a different beam. But this comes from, these neutrinos come from stop pions, right? And then muon decays. And so we have two different flavor components in the flux. We have electron and muon components, right? And so the idea here is that if you look sort of and you try to once again statistically separate these flavors, which is with the regime and we're right now, right? Because once again, you can't say that event came from muon neutrino, that event came from electron. You can only kind of statistically look at the spectrum and do this. So the question is, if you plot your flux average cross section for the electrons versus the flux average cross section for the muons, can you actually make a flavor separation at this point? Well, not surprisingly, at the moment you can't with the current data because we're only based upon 100 of events or so in coherent scattering. So the idea here is in the future, right? Here's kind of the standard model predictions for these. For where this would live. And then the idea here is you want to kind of squeeze this around the standard model prediction, right? And then you kind of get a measurement of flavor separation. And of course, if you measure that shifted in some way from the standard model prediction, then that's quite interesting in itself. So we want to kind of think about this in the context of flavors, right? And going forward. And this is a simulation that was done by Dan Pershey for different types of targets, an example of how that might work, right? If you have different targets, then you can, your standard model blobs would show up in different parts here. And I'll actually remind you too that the fluxes are the fluxed average cross sections are different from each other because the flux distribution is different for the muons and the electrons. So that's actually a systematic in this convolution here as well. So Bryce was talking about sterile neutrinos yesterday, and he was very excited about them, right? So there's actually a lot of papers on BSM and searching for non-standard neutrino interactions. Probably many people in this room have worked on this. But I kind of just following up on Bryce's talk yesterday, I just wanted to highlight why this flavor separation might be useful going forward. And so this is a paper we did with a student a couple of years ago, looking basically for just your standard 3+1 sterile neutrino model at coherent, right? And taking advantage of this electron component that exists in the data. So the idea is, can you statistically separate that electron component from the muon components and be sensitive to say the best in reactor neutrino anomalies? And it turns out you actually do, you can do pretty good. Okay, so the left here, well, that's given the current data and interpretation of the current data, right? A lot of that regime is actually still consistent with the 3+1 model. That's because there's like a little bit of a peculiarity currently in the coherent cesium data. So if you kind of squinted at that point, it was like a little bit lower than the standard model prediction. And that's what's driving that at this point. But we might be still in a statistics limited regime. But so then we ask, like, if we just extend the coherent experiment to sort of something reasonable that's going on in Neutrino Alley in the next few years to like a 1-ton projection, basically you could actually be sensitive to more or less this entire regime of parameter space. So I think I just kind of want to get across, this is kind of an independent way to check what's going on in this sector. And there's actually been also analyses done sort of in comparing to the LS&D anomaly. If you look at this Blanco et al. Paper, they actually did an interpretation along these lines. So my last point here, I won't go into too much details on this, sort of what's another future application of sevens. For a long time, when WIMP dark matter, right? We want to measure WIMP dark matter. How do we know that it's a WIMP? Well, okay, if you get a directional detector, right, there's a prediction for the direction from which the WIMPs will come from. So that could be used to confirm a dark matter signal. Well, I think now an interesting application of direct detectors with a directional sensitivity is actually just put them right, in Neutrino Alley, right, and try to use them to detect coherent scattering and try to understand the kinematics of sevens a little bit better here. So not only can you use it to understand the kinematics, you can actually use this to probe sort of different beyond the standard model effects, and that was discussed here in a paper we had a couple years ago. And one other reason I like this too, and this was actually done. So the Cygnus collaboration actually published a long paper on this recently. If you have the energy and the angular distribution of the neutrinos, right, this actually in principle gives you a sort of direct reconstruction of the neutrino energy, right? So they looked at this in the context of solar neutrinos. So this is actually kind of like a futuristic type Cygnus experiment that could detect directionality of solar neutrinos from the sun. And you can kind of just see here, here's the solar spectrum basically. So you're not talking about measuring just the nucleus and that energy. You're talking about now officially trying to reconstruct what's the actual neutrino energy. So I think there's actually interesting applications to think about going forward with this type of technology, bringing it to maybe looking at the survival probability of neutrinos and various other phenomena. So sorry, I've gone a little over. So that is all I don't really have any conclusions. I just hope I highlighted for you some opportunities going forward in the neutrino sector, sort of using sort of these detectors that we hope will come online soon, and the physics opportunities available. So, okay, any questions?
Thank you for this very interesting talk. Time for questions. Yeah. Andre.
So can you go back to your Borexino FPFX plot, the one coming out or just came out?
Yeah, sorry, it's a little busy, but yeah.
But so one is we have a very, very old paper about the plot on the left, which is like before oscillations existed and probably nobody remembers it.
Okay. I'll blame your former student, actually.
It's probably his fault.
Yeah.
But what is FE and how do you constrain FE?
So
I know the paper line just from because the radium 7 plots with pretty good precision.
Yeah. Right.
How would you constrain the electrons fraction? Is it from external information?
So yeah, that's kind of the game that we went through here, right? So the I forgot which one is which here. So unconstrained base. Okay, so how do you want to analyze the Borg-Sina? How do you want to? This is actually kind of an interesting point. Actually, maybe to help make the point, I can go back to the spectrum here. So how do you want to what do you assume? This actually came up. What do you assume when you where'd Borg-Sina go? Yeah, oh, that's Pandex. Oh yeah, what do you assume when you just analyze the spectrum about anything, right? You can put in like no assumptions at all on anything. That was that really long band, right? You can put in a prior value on the electron neutrino survival probability motivated by other experiments, right? Which was kind of, as you know, and that kind of like shrinks the band a little bit, right? So now we can go back here, right? And there we go. Yeah, so if you say I know absolutely nothing about nothing, right, you get sort of an elongated structure that effectively doesn't constrain any electron neutrino components at all. But then we're kind of thinking about this is like stupid because all the other solar neutrino experiments have like measured an electron component. So you have to like that information has to be in there somewhere, right?
Yeah, because somehow the hope is that this is the hope is that angle, that energy distributions are different for the electron scattering and the muon scattering.
Exactly. Yeah.
And the question is, how sensitive are you to that difference?
Exactly.
And again, that was our old paper, but
yeah.
But clearly, but you're still putting in some more external information.
We are putting in, yeah. So in the case where you shrink it in these smaller bands, we are putting in some external. And the question is how much external information you put in. We put in like I think the 5% was just motivated by sort of the width of that MSW band if you take the values of the measured parameters, if I remember correctly.
Cool, thank you.
Yeah.
Are there? Okay. Bruce. Yeah, Bruce.
Can you go to the oscillation plot from sevens? The sterile oscillation.
I put that figure in there for you, by the way, so I'm glad you asked.
You mean on the right plot?
So I think this was one was for a different target. So this one's for different types of assumed targets, like an argon target and a cesium target. Actually.
Yeah, but what you're saying is you're taking advantage of a difference between your ability to resolve the different flavors or something like that.
That's right. Yeah. So kind of let me like, yeah, I kind of went through this a little quickly, right? So the neutrino spectrum from muon decay, right? So the shape is for the different components are different, right? So the idea is, and also in sevens, right? You have like a prompt, and for the stop pion, right? You have a prompt neutrinos that come, and then you have the delayed neutrinos. So you have like two pieces of experimental information, right? You have the energy spectrum, which you're trying to statistically separate, and then you have the timing distribution. So you can kind of put that into a whole likelihood analysis, and that kind of like goes into here. I skipped all the details, but so when you put in all that information, the idea is, how sensitive can you be to that, like, kind of subdominant, if you will, prompt, delayed electron component? And that's the piece you're trying to pick out here.
Yeah. To in the same paper, you have like
that's right. Yeah. Yeah.
Thanks.
Yeah.
Just
Yeah.
Yeah, we are planning to do the new mu, but just. And those lines are one for sodium iodide, and the other one is for liquid argon. Okay.
Are there comments or questions?
Yeah, I should also mention too, we're running through the same analysis right now with the new germanium data to see how that looks.
Okay. If not, let us thank Luis again.